Kinetics is motion of an object under the influence of forces. Kinetics is what we use to find equations of motion, which is how an object behaves under the influence of those forces. Usually this will have external forces on one side and position, velocity, acceleration, the kinematics variables stuff on the other side. So we had different approaches to the equations of motion. We had Newton, who gives us sum of the forces equals mass times acceleration, and sum of the torques equals moment of inertia times angular acceleration. So that is one approach. We use Newton if acceleration is 0 or problem is simple. Then we had Lagrange. So that is the dt del L del S dot minus del L del S equals external forces for linear and d dt del L del theta dot minus del L del theta equals external torque. So we use this one for complicated systems. Like if they're nonlinear. Now in Newtonian kinetics, for translation, we said sum of the forces equals mass times acceleration, but really we can, because it's a vector, we have to split it up into 3 directions. So sum of the forces in x equals m ax, sum of the forces in y equals m ay, and sum of the torques around either axis of rotation or mass center. But for pure translation, then there isn't any, so they equal 0. For rotation, we can say sum of the forces in the r direction equals m times ar equals m r omega squared equals m v squared over r. Sum of the forces in the theta direction equals m a theta equals m r alpha. And sum torques on the origin equals moment of inertia around the origin times alpha, or we can sum torques around center of mass equals I center of mass alpha. So note that if using I around the axis of rotation, you must use parallel axis theorem, where I around the origin equals I at the centroid plus m d squared. So example that is like this. So you have I around the centroid, C, but this distance is D, and this origin is O. So IC plus md squared if you're rotating around an axis that is not through the center of mass. So whereas mass is resistance to linear motion, moment of inertia is from resistance to angular motion. And Lagrange's method uses energy, whereas Newton's method uses forces. So there are different types of energies. Energy can be dissipated, or it can be stored. So dissipated is path dependent. So if you think about if you're pushing something along the ground and there's friction on the ground, if you go straight from point A to point B, that took less energy than to push it if you went all the way around the room first and then to point B. And this is by non-conservative forces. Stored energy is path independent. So you just go from A to B and it doesn't matter how you get there. And it is by conservative forces. Examples of the non-conservative forces and dissipative types of energy are friction, drag, damping, and we call that W and C for non-conservative work. Now, stored energy can be stored by pushing and pulling. That's conservative work. It can be stored in a mass as kinetic energy. We can get kinetic energy of rotation or translation. And then finally, it can be stored in gravity or in a spring as potential energy. So we'll make our chart of the type, the force, and the work or energy. Now, remember that work equals change in energy. So energy at 1 plus work from 1 to 2 equals energy at 2. And we can rewrite that as potential energy at 1 plus kinetic energy at 1 plus work from 1 to 2 equals potential energy at 2 plus kinetic energy at 2. Now, if work equals 0, then energy is conserved. And in that case, energy at 1 equals energy at 2. And work equals integral of F dot ds from S1 to S2. F and S are vectors, so their dot product becomes a scalar. So now back to our chart. One type is gravity. Gravitational force is mg, and the gravitational potential energy is mgh, where h is the distance that above the origin that the object is. And then a spring force is k times s, where s is distance of spring stretch. So I'm going to write it as s minus s initial, where s initial is the unstretched length. And then that is, energy is 1/2 k s squared. Now in a mass, so that's kinetic, and if we have it translating, we know F equals ma, and so this is 1/2 mv squared. If we have a mass rotating, then really what we're getting is torque, which equals I alpha. And that kinetic energy is 1/2 I omega squared. If something is pushing or pulling, the force is given, it's P. And if P is constant, then we just have P times S is the work done. Otherwise, we use this integration formula if P was not constant. We have friction, which is mu times normal force. So the work by friction is mu in times the distance that it went, and that is negative. Friction does work against you. And then finally, drag. The drag force equals 1/2 rho CD v squared A. And that work is again negative. Drag force, we'll just call it FD, times pushing distance. Well, step one is always draw a free body diagram. So you might have friction, mass times gravity, normal force, maybe a pull. So you draw a free body diagram for every object. And include all external forces. Or torques. Then step 2 is assign coordinate frame. So we put X in direction of motion. Or line of impact if it's a collision. And then Y goes perpendicular to it. Or plane of contact. And always X follows the rope if there is a rope. So if you have blocks on plane connected by pulley, X follows the rope. Then finally, we write equations. So this could be Newton's laws, sum of the forces, sum of the torques. It could be work and energy. Energy at 1 plus work 1 to 2 equals energy at 2. It could be impulse and momentum. Or it can be Lagrange's equations, which is derivative of work and energy. And then finally, solve the equations. So you might need to rearrange or consolidate variables by kind of getting clever with geometry. Example of this is S equals R theta. Or something like that. Now, how do we know what approach to use to solve a problem? So what equation do we want to use? We start with check collision. Well, if there is a collision, then we check if there's an impulse. We remember that impulse is F delta T. So if F delta T exists, Then we use impulse and momentum. Which is mv1 plus integral of f dt equals mv2. If there is no impulse, then momentum is conserved. So we have MA, BA1 plus MB, BB1 for two objects A and B that collide equals MA, VA2 plus MB, BB2. And then we also use the E equation. E equals negative VA2 minus VB2 over VA1 minus VB1. And E has several different values. E can be 0, 1, or something in between. So if E equals 1, energy is conserved. This is elastic collision. E equals 0, the objects stick. That is a plastic collision. And if E is anything in between, they rebound, but it's not great. Some energy is still lost. That's inelastic. All right, now if there was not a collision, then we have to check what variables are in the problem. So what kind of stuff is it asking us to find? Generally, if it asks for acceleration, then we use Newton's laws. Sum of the forces equals mass times acceleration. Sum of the torques equals moment of inertia times angular acceleration. And if instead the problem asks for velocity or position, then we check if there are external forces. So are there external forces that do work on the system? If there are, then we use work and energy. Energy at 1 plus work 1 to 2 equals energy at 2. And we just have to remember for this that non-conservative work is less than 0, conservative work is greater than 0. And if there are no external forces, then energy is conserved. So energy at 1 equals energy at 2. And that energy can be a combination of kinetic energy or potential energy. And if E equals 1, for the conservation of momentum, then you can use conservation of energy if you want to, or if somehow you seem to have too many variables to solve for and you need an extra equation.